Good afternoon, everybody, and welcome to BSides Las Vegas Proving Ground. On this talk, Cyber Deception After Detection by Toru Shimanaka. A few announcements before we begin. I would like to thank our sponsors, especially our Inner Circle sponsor, Critical Stack and Valleymail, and our stellar sponsors, Microsoft, Secure Code Warrior, and Paranoids. It is their support along with our sponsor donors and volunteers that make this event possible. These talks are being streamed live, and as a courtesy to our speakers and audience, we ask that you check to make sure your cell phones are set to silent. If you have a question, use the audience's microphone so YouTube can hear you. Please raise your hand, I'll bring it over. With that, let's get started, please.
I'd like to thank you for giving me the chance to speak here today. I'm going to talk about my cyber deception. I'm Toru Shimanaka. I'm a cybersecurity researcher at Fujitsu for about 5 years. Before that, I was making a network switch for about 15 years. What is cyber deception? This is one of the most widely used definitions of cyber deception. It's proposed by Yoel, but he wrote as a definition of computer security deception operation. And this is a picture of original deception operation in Normandy landings with an inflatable dummy tank. The military think tank MITRE lists these 5 deception purposes. Diversion, direct an adversary's attention to a goose asset. Resource depletion, waste an adversary's time and energy. Uncertainty, cause adversaries to doubt the veracity. Proactivity, use deception technique to detect attacks. Intelligence, observe adversary's behavior to get his information. Our main deception purpose is this intelligence. Many cybersecurity textbooks dictate that when a compromised endpoint is discovered, it should be disconnected from the network to prevent further damages. Of course, that is reasonable and safe practice in most cases. But it means missing out of obtaining valuable intelligence, such as adversaries' TTPs, tactics, techniques, and procedures, and purposes and intentions. And it also missing out of denying the attacker learning. In other words, when an attacker knows for sure he was detected, he can learn from his failure and come back again using more sophisticated tools and techniques. And textbooks also dictate, when a compromised endpoint is discovered, observe the attacker until you are sure you can remediate 100%, then remediate. That may be true, but can you track everything the attacker does? That's why this method has some risk still to your company. What if you could track the attacker, but without risk? Well, we are greedy. That's why we want to both safety by disconnection and intelligence by attack continuation. So this is a plan for achieving our greedy objectives. There are 3 elements to the idea. I'd like to explain how these elements are realized later. This is, so to speak, cyber deception after detection. We are interrupting between links 6 and 7 in the cyber key chain. Here is the deepest part of the key chain, and it's after the attacker has the command and control. It's very good because it's very expensive to the attacker. He already invested a lot. First, we prepare the deception network as a safe observation environment to protect the operational network. Safe means isolate the compromised endpoint to the deception network that is out of operational network. Okay, next I will explain the deception network or the ONET or DNet. The DNet is configured identically to the operational network or the ONET. The DNet has same network topology as the ONET, and hosts have same host names and same IP addresses corresponding to host in the ONET, except for MAC addresses. I will explain the reason later. The ONET and the DNet are connected by open-flow switches, and packets are controlled and related by software. OpenFlow is one of software-defined networking implementation. In the ONET, sensitive information has been deleted and fake information that confuse the adversary is embedded. And you can place many sensors and observe adversary's behavior in detail. The other two items are about software-controlled packet transfer. Using OpenFlow functionality, such communication between the compromised endpoint and the ONET to the DNet. That is, communication on the local network continue uninterrupted between the compromised endpoint and the other machines. But the other machines are actually turning into shadows in the DNet. Also, ensure that all communication between the compromised endpoint and the C2 server is not interrupted. This way, the attacker doesn't notice our cyber deception. This figure shows the software-controlled packet transfer that we aim. Suppose a compromised endpoint, in this case PC22, shown in red, is discovered. The communication between the compromised PC22 and C2 server continue without interruption. The communication between the compromised PC22 and ONET are transferred to the DNet. These software packet control allow us to keep the adversaries unaware of deception. This is our system's attack transfer mechanism. Initial step is detect a compromise. In this case, we detect an endpoint compromised because an attacker accessed a decoy file. The next step is preparing the DNet. The DNet was already made identically to the ONET. Based on the JSON file that defines the network configuration of the ONET and DNet, the deception controller turns off the shadow of the compromised endpoint in the DNet and create a script which sets the flow table using REST APIs. We implement the REST APIs as the northbound interface to the OpenFlow controller and execute this script and request the OpenFlow controller to set flow tables to OpenFlow switches. We implement our packet control and relating strategy using OpenFlow flow table. In general, OpenFlow is considered our standard for separating control from forwarding, but my perception is different. OpenFlow is a technology that opens up to everyone to secret that only switch software engineers keep. The secret is that switch ASIC can rewrite the packet, add something in the packet, and delete something from the packet. Having built switches for many years, I know some of these secrets and use them in this project. So, flow table consists of flow entries. These three are commonly used. Match field, its entry is a rule to match against the packet. The rule uses the ingress port and packet headers such as source and destination IP address, source and destination MAC address, source and destination TCP port, and so on. Priority, its entry is matching precedence of the flow entry. Instructions, its entry is a set of instructions for the packet, for example, to rewrite the packet and change the output port. For example, this flow table means if a packet comes in from port 1, then output packet via port 3 and port 4. Next flow table means if a packet has destination IP address 192.168.10.10, then rewrite the address to 192.168.20.30 and output via port 6. If the packet designated to 192.168.10.100 comes from port 1, this packet is transferred to the port 3 and port 4. But if the packet designated to 192.168.10.10 comes from port 1, the destination of this packet is rewritten and transferred to the port 6. Here are our packet rewriting strategies. The difference between the ONET and DNET is host MAC addresses. This is the key to control packet. Strategy 1, rely the communication on the local network. Strategy 1 use the compromised endpoints MAC address as the match rule. And we are rewriting not only the MAC address of the Ether header, but also the MAC address information in the upstream. If we use IP address as a match rule, it would generally work for UDP, but not for TCP. Strategy 2, consider the communication from the compromised endpoint to the router. It means to other subnetwork. By setting strategy 2, access from compromised endpoint to the internal network can be isolated to the DNET, and access to the C2 server can be maintained. Let's see what happens for the TCP communication from the compromised PC22 to the next PC21. According to the flow table set in this OpenFlow switch, the destination MAC address of the Ether header returned to MAC address of PC21 shadow and transferred to the DNET port. On receiving a new TCP packet from PC22, the PC21 shadow broadcasts an ARP request. The source MAC address in the Ether header and the ARP information are returned to the real PC21's MAC address and transferred to the port of the compromised PC22. By this mechanism, the compromised PC22 misunderstands that the response came from the real PC21, and things go on as such. This is how even the TCP communication between compromised PC22 and the ONET could be completely isolated to the DNET. The packet address to other subnetwork has the router 1 MAC address as its destination. If We use strategy 1 to this packet. Strategy 1 simply relay the destination to the MAC address of the router 1 shadow and forward the packet to the DNet. It works fine for the packet address to the intranet. However, strategy 1 transfers the packet address to the C2 server to the DNet. So we add strategy 2, the packet address to the C2 server are forwarded to the internet. This figure here shows the flow table set in the open flow switches for one compromised endpoint. Expand the flow table for R. This is a part of the textual representation of the flow table for R. Expand the flow table for other packet. Expand the flow table for keeping connection with C2 server. And so to summarize, we successfully built DNet. We switched over communication to DNet with some packet magic. We managed to continue communication with C2 server after moving the compromised endpoint to DNet. And the attacker can still operate as if nothing changed on our network. Well, next, the proof of concept. The most important objective is to keep adversaries unaware of the cyber deception. The conditions are as follows. The attacker maintains control of the compromised endpoint from their C2 server, transferring the network activities of the compromised endpoint from the ONET to DNet. Command executed by attacker on the endpoint, and the network must give identical result before and after DNet transfer. So we did a POC from the attacker's point of view. We create a script of post-compromise activities, and we execute the script from the C2 server's console before and after deception activation and compare the result. This is our POC environment. One server provides a virtualized environment for the ONET and the C2 server on the internet. And another server provides a virtualized environment for the DNet and the deception network management. Those are POC results. The automated attack script produced exactly the same result before and after deception. And the session between the compromised endpoint and C2 server remained uninterrupted during and after deception. I will conclude this presentation. Our objective is to create an environment to observe the adversary's attack safely and covertly, and keep the adversary unaware of deception. For that purpose, we created a deception network and manipulate the packet using SDN technology. As a result, the adversary cannot notice any difference before, during, and after cyber deception. And we have created an environment to observe the attack safely and covertly. These are future research. Our DNet seems that initially it's convincing to an attacker, but how does it remain convincing after 2 weeks or months? We need work to ensure that the DNet remains realistic in the eye of an attacker over time. Next are resource reduction of DNet and observation method for the DNet. They're almost same as problem of HoneyNet and honeypot. I think it's red ocean area, so I don't really want to do that if I can, to be honest. But I think there's a good way to do it. Next is IPv6 support. This is more complicated than IPv4. I've already finished POC and I'm submitting a paper now. The last is the combination with attack detection by deception. The attacker was overwhelmingly dominate the defender because the defender just wait passively without knowing what kind of attack is taking place. But if this combination is realized, we can reverse the situation. If the attacker is caught in one of many traps, the defender will win. This means for the first time in the history, the defender has an advantage over the attacker. That's all. Thank you very much, and thank you, my mentor, Klaus. If someone would like to know more, please refer this paper. And if you have any questions, I'm sorry I'm not good at English, but I will do my best.
Any questions? Okay.
You mentioned this is hosted on a hypervisor for Open vSwitch and OpenFlow. Are you using like a VMware-based thing, or is this?
Yes, VMware.
Yeah. Okay. Thanks.
Another question? No? Okay, thank you. Thank you very much.